forward to hearing Roger's talk, and thanks.
Thank you, Sean. So I'm talking about evaluating generative models from the lossy compression perspective. And this will cover essentially two papers. First one is a paper we published 3 years ago in iClear on the quantitative evaluation of decoder-based generative models. This is primarily the work of Liu and Thierry Berda. And the second half of the talk will be on new material, which will hopefully put up an archive in a couple of weeks. And this is on evaluating lossy compression rates of degenerative models, primarily the work of Sheldon Huang and Alireza Makhzani. And so why are we interested in evaluating compression rates of generative models? Well, we know that, that in the last few years, generative models have been able to do amazing things. So we know that generative models have been able to do amazing things in terms of generating convincing-looking images. So here's some examples from the Big GAN model. We're not necessarily only interested in generating images, right? We desire a lot of other things from generative modeling. We might like to make sure that our model actually captures the full distribution, or we might be interested in many representations and things like that. And so what are some other metrics that we might want to use? And one particular failure mode of just looking at samples is that the model could just be memorizing the training set, right? So here we have two different models. One model is an actual model that was trained on MNIST. The other one consists of taking a random training example from the data set. Now, if you look at GAN papers that are published, it's not actually true that they only show samples, right? There are quantitative criteria that they tend to measure. So in particular, the most popular ones are probably inception scores and Fauché inception distance, or FID scores. So these are quantitative criteria, but at the end of the day, they're still grounded in the perceptual quality of samples. So if you look at how they're justified in the literature, they're justified in terms of giving a good match to perceptual quality. So it's not that these metrics tell us something that the samples don't. It's more that looking at lots of samples is a lot of work, and we would like to be able to automate that process.
Right. So, so basically, they showed that inception scores could be misleading and gameable in various ways, and it's sort of the ways you'd usually expect whenever someone introduces a new metric. And so it'd be much more satisfying if we could evaluate generative models in terms of things like likelihoods, which have been vetted by statisticians for decades. And there's another very interesting problem that was pointed out about GANs. So there's a paper by some people at MIT last year where they would basically take an image from the validation set, so it's drawn from essentially the same distribution that the GAN is trained on. So they would take this image and they would optimize the noise variables in order to match that image as closely as possible. So for each of these pairs, you see the original image on the left and the closest match on the right. And you see an image that looks fairly plausible. I think it would probably do pretty well in terms of FID score or inception score, but it's missing an important object in the scene. So it's basically omitting whatever is the most difficult part of the image to model. So this is the failure mode that I'll return to later in the talk. And so can we evaluate these models in terms of likelihoods? And when I talk about likelihoods, I just mean the probability that the model assigns to held out data. And in some cases, we can't compute them exactly, but we can approximate them, for instance, using the elbow for variational autoencoder. And when we're dealing with supervised regression problems in the Bayesian framework, like GPs or Bayesian neural nets, it's pretty common to compute some sort of likelihoods. So whenever we can compute likelihoods, we almost always do. When it's not convenient to compute them, we can usually come up with some reasons that we never really wanted them anyway. And so what are these reasons? So when we're talking about models like GANs, there's actually a conceptual problem with even computing likelihoods at all. And Stefano alluded to this in his talk earlier today, and that's that models like GANs have low dimensional support. So they only put probability mass on a low dimensional manifold. And that means that if the data doesn't lie exactly on this manifold, then the likelihood will be 0. So it makes no sense to even try to evaluate it. So what can we do about that? Well, what they've sometimes done in GAN papers, as the approach I'll take in the first part of the talk, that's to impose some sort of noise model. So just pick your favorite noise model, like spherical Gaussian, and assume that the data doesn't come directly from the model, but it comes by sampling from the model and then adding some noise to whatever was produced. So this at least defines a valid density over the data. And so you can evaluate the probability density at any particular data point, and it'll be non-zero. So at least conceptually, it makes sense to evaluate likelihoods. Unfortunately, it's not a very satisfying solution because Gaussian noise is a very poor match to domains like images. And so this approach generally won't be competitive with, let's say, autoregressive models, right? So it gets penalized a lot by the failure to match the details of neighboring pixels and things like that. So I'll come back to this in the second half of the talk. But for now, let's just go with the Gaussian observation model and see what we can do with it. So in order to evaluate P of x, we have to compute this integral. We have to integrate out all possible values of the noise variable z. So it's a very high-dimensional integral, and it's a fairly complicated one too, right? It involves this whole generator network in the definition. And so how do we actually evaluate this integral efficiently? And if we think we've done that, how do we actually check if we got the right answer or not? So we have these two problems of low dimensional support and intractable integrals. And I'll first mention a very cute solution from a few years ago. There are two papers that came out about the same time where they both trained tractable GAN models. So they used invertible architectures or flows, where it's tractable both to invert the generator network and also to compute the determinant, which you need to compute the likelihoods. And so they could train this using the GAN criterion instead of the usual maximum likelihood criterion, and see how well does it actually reflect the data distribution. And so one of these papers actually estimated 10 to the 15 bits per dimension on the SLUB-A data set. And this is pretty bad, right? So the uniform distribution gives 8 bits per dimension, right? So this is essentially saying that the GAN model that you trained is 100 trillion times worse at lossless compression than the uniform distribution. So mathematically, it's probably true in some sense, but I don't think this is really the right conclusion. I think any reasonable measure should tell us that we've actually learned something useful from training the GAN. So even though Gaussian observation models are a little bit of a straw man, at least they allow us to only capture the data point approximately. So let's run with that and see if we can get these Gaussian observation models to work. So for the first half of the talk, I'll be talking about estimating log likelihoods for implicit generative models. So I'll introduce the classic algorithm annealed importance sampling, which is the main workhorse we use to get these estimates. And then I'll talk about how to validate our estimates. So measure the amount of error in our estimates using something called bidirectional Monte Carlo. And then we'll actually apply this to compare different generative models and detect things like dropped modes. So in the second half of the talk, we'll kind of shift gears, and rather than looking at log likelihoods, which are a measure of lossless compression, we'll be looking at lossy compression. and evaluating rate distortion curves of implicit generative models. So I'll talk about why we want to do this and how we can actually use the same techniques to estimate the RD curves. And we'll see that we can actually learn a lot more from this than just from scalar log likelihood values. Okay, so annealed importance sampling, or AIS, is a classic algorithm, which is still basically the state-of-the-art generic method for estimating partition functions. And the way it works is you have an intractable target distribution, PK, and this could be the posterior distribution of the latent variables conditioned on the data. And we also define a tractable initial distribution. So this could be the prior distribution or a uniform distribution or something like that. And we gradually transform the initial distribution into the target distribution. So this is known as annealing, because we can think of the initial distribution as being a high temperature distribution, and as we transform it to the target distribution, we're gradually lowering the temperature. And so the generic choice of how to do this is shown at the bottom of the screen. So typically we can take geometric averages of the initial distribution and the target distribution. So in the case of generative models, we essentially define the distribution to be the prior times the likelihood term raised to a power. So as the power goes from 0 to 1, we're annealing from the initial distribution to the target distribution or the posterior. And so the way this algorithm actually works is that for each of these intermediate distributions, we assume we have an MCMC transition operator. And the generic choice is probably Hamiltonian Monte Carlo, or HMC. There's also an algorithm introduced to our field by Radford Neal back in the 90s, which is still one of the best ways of doing generic inference in continuous models. It's what Stan uses, for instance. So we assume we have these MCMC operators for each of our intermediate distributions, and we essentially alternate between these two steps. So we have one step where we update the weights of the model using a particular formula, which won't be important for this talk, and we move to the next distribution, so we reduce the temperature. And then we apply our MCMC operator. And so we keep adjusting the temperature and applying MCMC and so on. And eventually, we'll end up with something that approximates a sample from the intractable target distribution. And as we do this, as we keep track of these weights, we also end up with a weight whose expectation is the ratio of partition functions between the initial and target distributions. So at the end of the day, what this gives us is an unbiased estimate of the partition function of the target distribution. So in the case of evaluating generative models, that will be, so we have an unbiased estimate of the probability assigned to a particular data point X. And so one way to think about this algorithm, so here we're doing inference over one-dimensional distribution. So we have a simple Gaussian initial distribution and bimodal target distribution. And each row of this figure is showing one step, and our MCMC operator is just a simple symmetric Metropolis Hastings kernel. So we're taking small steps, and the distribution is gradually transforming to resemble the target distribution. Unfortunately, in this case, we don't get it quite correct. So the final samples are misallocating probability between the two modes, but it's kind of roughly capturing the shape. And we'll see the implications of that in just a bit. So why does AIS work? Well, the original justification of it was that we can view it as doing importance sampling over an extended state space. So if you keep track of all of the individual states visited by the algorithm, then when you run AIS, you're following the blue arrows. So you're following each of the MCMC transition kernels in order. But we can also define this hypothetical reverse chain. So we start with an exact sample from the target distribution pk, and we run all of our transition operators in the reverse order. And the so the value of zk in that reverse chain will actually, that will be a sample from the exact target distribution. And so AIS is essentially doing importance sampling over this extended state space consisting of all of the states visited by the algorithm. And so we're doing importance sampling over this entire state space, which also gives us an importance weight over the final state. And so this basically shows that it gives an unbiased estimator of the partition function of the target distribution. And it probably seems kind of funny to be doing importance sampling over this expanded state space. But if we think about the cartoon example from earlier, so we have the forward chains on the left and these hypothetical reverse chains on the right. And so if we're doing importance sampling over the space of trajectories, the trajectories from the forward model basically resemble the trajectories from the reverse model, except that the allocation of mass between the two modes is slightly different. And so we're sort of doing importance sampling over a small discrete space, which is a pretty reasonable thing to do. So that's the classic AIS algorithm. So that's what we'll be using to estimate partition functions. But there's this big question of how do we actually validate our estimates? And so you might have read The Hitchhiker's Guide to the Galaxy. So they built this great big computer, and they asked it, what's the answer to life, the universe, and everything? And it turns away for 1 million years and eventually returns the answer 42. And we're kind of in a similar situation when we evaluate likelihoods, right? We ask, what's the validation log likelihood of my generative model? And AIS turns away for a long time, and it eventually returns the answer 991.4 nats. So, is this the right answer? Normally in machine learning, we have some idea of what sort of behavior to expect from our algorithm. If we get something that's totally wrong, there are often red flags we can pick up. Not so true when we evaluate log likelihoods. And there's actually an instance where some people submitted or published a paper studying Bayesian models of prawn behavior, and it actually turned out that their likelihood estimates were wrong in a way that affected their conclusions, and they had to retract the paper. So how can we avoid this? How can we be confident of our log likelihood estimates? So, so an important piece of this is that, so I said the AIS gives an unbiased estimate of the partition function. And if you have an unbiased estimate of z, you can actually show that it behaves like a lower bound on log z. In particular, through a straightforward application of Markov's inequality, you can show that it's very unlikely to overestimate log z by very much. So, so estimators like AIS essentially behave like lower bounds. And this is sort of intuitive because if you are able to explore a subset of the input space, you might capture some of the modes of the distribution but miss other modes. And if you fail to account for the mass of those modes you missed, then you'll underestimate the partition function. So that's the intuition for why it's easier to get lower bounds than upper bounds. So how can we get upper bounds? So conceptually, we can take this picture I showed you earlier of AIS as importance sampling over these extended state spaces, right? The entire trajectory of states visited by the algorithm. We can swap the role of the two distributions. So if we could actually run the reverse chain, so start with an exact sample from the target distribution and run the MCMC operators in reverse order, we can do importance sampling to the forward distribution. So just reverse the role of these distributions. And if you do a bit of algebra, it turns out this actually gives you a stochastic upper bound on the log partition function. So that's great. We have an upper bound that we can combine with our lower bound. The catch is that running the reverse chain is generally intractable. We need an exact sample from PK in order to be able to run it. And if inference is intractable, how are we going to get an exact sample? It actually turns out that if we're evaluating generative models, there's a way to do this for data generated from the model. So the way to think about this is if you have a joint distribution over z and x, as defined by the model, there are two ways to sample from this joint distribution. Either you can forward sample, so sample z from the prior, and then sample x from p of x given z. So that's one way to get a sample from p of z comma x. But conceptually, you could also do it in the reverse direction. So first sample x from p of x, and then sample z from the exact posterior. Right? So p of z given x. So these are two different ways of sampling from the same joint distribution, which means that when you forward sample from the model, then whatever z that you use to generate the data is actually an exact posterior sample conditioned on x. So for data that's generated from the model, we have available to us exactly one posterior sample. And that's all we need to run the reverse chain. So to summarize, what we do is we sample z from the prior distribution, like a uniform Gaussian or whatever we're using, sample x from p of x given z. We get a lower bound on log p of x by running AIS forwards, and we get an upper bound on log p of x by running AIS backwards. And so the gap between these two bounds is what I call the BDMC gap. So this is something that we can estimate on synthetic data. But if the generative model is pretty reasonable, it's pretty representative of real data, then this should give us a good idea of how accurate our log likelihood estimates are on real data. So we actually have a way of validating our log likelihood estimates. So it's a very unusual property of AIS that not a lot of people know about. Okay, and so how can we apply this to GANs? Well, our approach estimates the log likelihoods in kind of a very generic way. We just combine AIS with HMC. This is sort of your go-to partition function estimator and your go-to MCMC algorithm. But we can validate the accuracy of our estimates on simulated data using BDMC. And so we can actually tell if we got accurate results or not. We know, how many steps of this algorithm do we actually need to run. And so we evaluated various implicit generative models on MNIST. And I'm loosely considering VAEs to be an implicit model here, right? They're not actually implicit because you have an encoder model that does inference. But for the purposes of these experiments, we're ignoring the encoder, and I'm just treating the decoder as the generative model. And so we're comparing all these models on equal footing with the same inference algorithm. And we impose the same spherical Gaussian observations on all these models, including the VAE. And so when we evaluate the likelihoods of these different models, so we have the likelihoods as estimated by AIS on the training data and the test data, and we also have the BDMC gaps that are the measure of error in our estimates. And so what we see is that we can actually estimate the log likelihoods accurately. So our BDMC gaps are usually less than 1. There's one case where the error is high as 10, but which is still basically accurate enough to draw scientific conclusions that we're interested in. And so the one thing we can measure is that as you go to a larger model, so increase the latent dimension, you get a much higher log likelihood. It's not too surprising. And we also see that the variational autoencoders achieve much higher log likelihood than the GANs and the other model that we considered, the generative moment matching networks. And so it's not surprising that the VAEs do better. Also, the VAEs are trained essentially, well, they're trained on the elbow, which is an approximation to the likelihood. So we'd expect them, so likelihood-based evaluation should favor VAEs. But the size of the gap is actually pretty large. Another thing we notice, so if we compare the training versus test log likelihoods of the GANs and GMMNs, there's actually no statistically significant difference between them. So we actually don't see evidence of overfitting in the context of these models. So we can basically rule out the possibility that they're just memorizing the training examples, at least on MNIST. All right, so why are the likelihoods so much worse for GANs than for VAEs? Well, one of the things that we can immediately notice if we look at samples is that they misallocate the probability mass between modes. So you see a lot of instances of ones. I think about 40% of the generated samples are ones, and I think only one of the 100 samples was a 2. So it's a serious misallocation of probability mass. And when people, so in the GAN community, there's a lot of discussion of mode dropping, and this is often equated with missing one of the 10 MNIST digit classes if they're working with MNIST, right? So it's a very simplistic notion of mode dropping. We'll see it's actually, what's happening is actually more subtle. And so the effect that I just showed you is actually too small to explain why the GAN underperforms the VAE in terms of likelihood by 350 nats. And actually, if you go through the calculations, if this were all the GAN were doing wrong, that would only hurt it by less than 10 nats in terms of the likelihood. But it was actually worse by 350. So it does seem to be a mode dropping problem, but it's much more subtle than the one we usually think about. And so we can actually use the same techniques that I just described to visualize posterior samples conditioned on the observations. Right, so we take an image X and we approximately sample Z from the posterior P of Z given X, and then we run the generator network to see what that sample looks like. Okay, and so I won't go into the details, but BDMC can be used not just to validate the log likelihood estimates, but also to validate the quality of the posterior samples. And so we can actually show that the KL divergence from the true posterior is at most 1. Okay, so question, how do you do the calculation to measure the loss in likelihood due to mode imbalance? Right, so this is basically saying that if the network gets exactly the right distribution, except that it misallocates mass between the digit classes. So instead of producing 2s 10% of the time, it's producing 2s 1% of the time. Then it's paying log of 10% divided by 1%. So probably about 2. So paying 2 additional nats each time it tries to model a 2. Right, so if that were all we're doing wrong, that wouldn't contribute very much in terms of the log likelihood score. Right, so when we visualize the posterior samples, so we have validation examples in the top row, and we have the posterior reconstructions produced by various models. And the 2s and the 8s seem to be the hardest MNIST digit classes to model. And and we notice that some of the models aren't able to represent the original image, right? So if they were able to represent it, then the posterior would probably be concentrated on something very close to it. But we see that when we feed it an 8, the GAN10 produces a 5, and so it's not representing anything close to that particular 8 in its model. This also happens even on training images, so it's not just a matter of overfitting. So here are examples of 2s from the training data set. and we see that so the VAE can reconstruct them perfectly, as we would hope. It's an autoencoder, it's trained to reconstruct things. But the GANs, a third of the time, they're not able to approximate the image, right? There are some cases where it produces a completely different digit class. So what we see is that it's not completely ignoring the mode of 2s, right? It's able to generate some 2s. It's just not able to generate all of the 2s. There are particular styles that it doesn't learn to generate. And so it's actually missing not the entire mode of 2s, but particular submodes of 2s. So this is something that we can learn from looking at likelihoods and posterior samples. Okay, so that's the first part of the talk. Maybe I'll pause for a couple minutes for questions so far.
So there's an earlier question, which was, okay, I always answered. It was just how you do the calculation, measuring the loss in likelihood.
Okay, great.
Yeah, go ahead.
Okay, so we talked so far about log likelihoods, and you can think about log likelihoods as a measure of lossless compression. So how many bits does it require to communicate a particular image exactly pixel by pixel? And so Gaussian log likelihood corresponds to a particular coding scheme for the pixel values. But if we're modeling images, we don't necessarily care about the details of every single pixel. We might be satisfied if we can efficiently code for something that's close to the original image. So maybe in terms of pixel-wise mean squared error, or maybe you happen to have a metric that you think captures the semantic properties of the image. So we might be happy if we can get close. So the problem of, so it's one of the problems with just measuring likelihoods is that they don't use the metric structure over images. They don't know that one image is close to another image. And so Gaussian distance has been pretty popular in our community in the last few years. And one of the main advantages over likelihoods is that it can make use of the metric structure over images. Unfortunately, Gaussian distance is very hard to estimate in high-dimensional spaces. In fact, we might even be farther from estimating it accurately than we are from estimating log likelihoods. So can we do anything that's kind of similar to likelihoods, but uses the metric structure over images? And that's where lossy compression comes in.
Yeah, and there's one more question. So the question from Jeev, just how do we, what do we read into these takeaways when you have like relatively simple architectures?
Yeah, I mean, I think it's still useful to evaluate algorithmic contributions on smaller data sets and simpler architectures if it tells us something new that we don't learn using whatever ways we evaluate ImageNet models, right? So, so I think our community is very excited about doing things on ImageNet, but if you're introducing a new technique and you're only able to do quantitative evaluation on smaller architectures and smaller data sets, I think it's still worth doing that to measure if you've really improved things. Maybe, right, so Sanjeev says maybe the models improve at different rates if you change depth 3 to 6, right? So I mean, certainly, as you move to a different data set and change the architecture, the optimal hyperparameters will change and things like that, right? So you can't just assume that the conclusions will carry over, but it's all about doing science and understanding what are the reasons for things changing, so that you can learn conclusions that will generalize to new situations. So Lee asks, is the calculation on the loss and likelihood due to mode imbalance a lower bound because of the assumption that each class consists of a single mode rather than multiple modes? So when I was describing the kind of naive version of mode collapse, I was kind of equating modes and classes, but then I was arguing later that modes aren't exactly the same thing as classes of the image, right? So I was talking about the lower bound on loss and likelihood. That was for the naive view of mode collapse. All right, so what do I mean by lossy compression? So the basic setup is that we have X, which is an image. So we assume it's a sample from the data distribution. And we have an inference procedure, I'll write as Q of Z given X. And I'll come back to what that actually is later. But let's assume that we have some inference procedure that gives Q of Z given X. So we sample from that. And then we run so we pass that through our generator network, F, and that gives an approximate reconstruction, X hat. And so we assume we have a distortion metric that we can use to evaluate how closely X hat matches X. And so this could be a Euclidean mean squared error, and that's probably the most generic thing to use. But you might also use something you think is a better match to perception or semantic similarity or something like that. So you could use the structural similarity, you could use the distance and the hidden space of a neural net. There are a lot of choices available to us. So the choice of distortion metric is, the idea of the distortion metric is fairly straightforward. So we also have the other term we call the rate. And I define the rate here as the KL divergence from the approximate posterior to the prior. So it's exactly the same notion of rate that we use for things like variational autoencoders. And this basically says what's the cost of communicating X hat using a coding scheme derived from Q of Z given X, right? And this is kind of motivated by the idea of bit stack encoding. If you don't know what that is, it's not so relevant to the rest of this talk. I highly recommend checking out a tutorial video by Peter Beal that explains it really well. So we're not actually doing lossy compression here. So even though good compression schemes exist for lossless compression, we've not yet come up with a good technique for actually doing lossy compression using our generative models. So what we're actually doing is just measuring, in principle, how much lossy compression is possible. Okay. So, right. So what's the rate distortion objective? Well, we're basically trying to minimize the rate, so code for the image in as few bits as possible, subject to a constraint on the average distortion. So you have this constraint that the expectation, if we sample X from the data distribution, the expectation of the distortion is less than or equal to some value D. So that defines the rate distortion function. So the rate as a function of D gives the minimum value of the rate subject to the distortion constraint. So that is fairly awkward because the constraint ties together all the different values of X. But fortunately, the Lagrangian is separable as X. It's separable in X, right? So basically convert the constraint to a penalty, and we can push the minimization over Q inside the expectation. Right, so now we have a separate optimization problem for each individual image. So we're asking separately, how do we, for this particular image, minimize the rate plus some penalty on the distortion. So that's what it is mathematically. Let's see what it actually looks like visually. So here we have a cartoon where the box on the left shows the input space, and we have a generative model that generates on a one-dimensional submanifold. And we have a prior such that if we sample from it, it'll produce the distribution shown in blue. And so that is one choice we could use for a posterior distribution, Q of z given x. And if we just use the prior, then our rate will be 0, right? Our KL divergence from the prior will be 0. But the distortion will be pretty high. So distortion will be the average squared distance from the sampled points to the test point. So that's one choice of distribution we can use. Another choice would be this one, but it's a very bad one to use because, well, so the rate is non-zero because it's not the prior, but also has higher distortion. The better choice could be this one. So we're paying some bits, but we're getting closer on average to the test point. If we pay even more bits, we can get even closer to the test point. And so we have different points achieving different trade-offs between the rate and the distortion. And if we look at the optimal frontier, that gives us the rate distortion curve. And that's the best possible rate we can achieve for any distortion. And so the vertical asymptote, that corresponds to the minimum possible distance we can achieve to the test point. So that's essentially the distance of the projection onto the manifold. So that's the smallest possible value of the distortion that we can achieve. And so what happens if we change the model, right? So here's one generative model that achieves one particular rate distortion curve. If we improve the prior distribution, then we can achieve the same distortion with a much lower rate. So if the prior is closer to the posterior, then we're paying fewer bits to encode the image. But it levels off to the same value because we're still restricted to the same manifold, and so the projection will be the same value. So instead, we could improve the model by changing the manifold so they can get closer to the test image. So that will actually be able to achieve a smaller distortion, but you might still need a large rate in order to do it because the prior is still not very good here. And so we see two different ways that we can improve a generative model, and these have different effects on the rate distortion curve. So we're not just measuring a scalar value here, we can actually get sort of more dimensions of insight into what our generative model actually knows. All right, so that's what we're trying to achieve in principle. How do we actually do this? So I showed you the Lagrangian for the rate distortion objective. So we're minimizing the linear combination of the rate and the distortion. And you can show that the optimal solution to this objective has this particular form. So the optimal Q of z given x is proportional to the prior P of z times e to the minus beta times the distortion. So that's the optimal solution. And we can think about how this varies as a function of beta. So if we set beta equals 0, then we have the prior distribution, right? So if we're not penalizing the distortion at all, then we can minimize the rate by just using the prior. If we set beta to infinity, then it would that only cares about minimizing the distortion, doesn't care about the rate, And so it'll basically give a point mass on the argmin of the distortion. And so it's interesting also to notice that if D is the Euclidean squared error, then this is actually equivalent to the posterior over Z if we assume a Gaussian observation model whose variance is beta inverse. So it's kind of funny because Gaussian noise model is this horrible thing, right, that completely doesn't describe images, but squared error is a fairly natural distance metric to use. We often use squared error when we're doing some sort of image processing, and so using squared error as a distortion function will actually turn out to give a very similar optimization problem as evaluating the log likelihoods. Of course, we don't have to use squared error, and of course, we don't even have to use a metric that gives a probabilistic interpretation. So we're free to choose more perceptually valid metrics if we want to. And so we can actually approximate the solution using AIS. So it's interesting to compare the optimal solution to the rate distortion objective versus the intermediate distributions from AIS. And these are basically the same thing, right? And so it turns out that when we were using AIS to estimate log likelihoods, we've actually been tracing out the RD curves all along, and we just didn't know it. So for exactly the same computations we were doing before to get likelihoods, we don't just get a single value. We can actually get the whole RD curve. So that's not quite true because we need to show that we actually get a bound on the rate distortion curve. I'll skip over this for lack of time, but basically using the same sort of derivations that justified AAS for estimating likelihoods, we can actually show that we get an upper bound on the rate distortion curve. All right, so we can estimate the whole RD curve using basically the same computations we were doing before to get likelihoods. So we get a provable upper bound in expectation, and we have the usual guarantees of AIS that as you take enough steps, then eventually you'll converge to the true curve. And as I'll show, it seems to give very accurate estimates in practice. So one simple method of validation would be to estimate the curve for a tractable model where we can actually compute the curve exactly. So here's a linear VAE. We can compute the exact curve analytically, and when we estimate it using AIS, it's basically visually indistinguishable. Unfortunately, we're not able to get the exact RD curves for more interesting models. But another thing that we can do is we can try to damage the model in various ways and see if we can detect it using the RD curves. So let's say we've trained up a model. I think this is a VAE. I don't remember specifically. But we've trained up a model. And what we're doing here is we're taking a mixture of the trained model with a garbage distribution. So I think it's just a very broad Gaussian or something like that. And so the green curve shows the RD curve if we use the true distribution. If we average it with the garbage prior in varying degrees, then the RD curve shifts upwards. Right. So because more of the probability mass is allocated to a bogus prior, it requires more bits in order to get close to the data distribution. But alternatively, we could damage the model by blurring the generated images. And so if we do that, then it doesn't affect the rate so much in the low rate regime, but it prevents us from achieving a low distortion. And so it has a very different effect on the shapes of the curves. All right, so what if we apply this to actual models that we've trained. So here we're comparing different MNIST VAEs. So these have, these differ only in the latent dimension. And so we see that as we move from 2 latent dimensions to 10 to 100, the curves are shifting up and to the left. So the fact that they're shifting to the left means that we're achieving lower distortion. So you certainly hope that would be true. So as you add more latent variables, you ought to be able to encode images to a lower distortion. But the curves are also shifting upwards. This seems to indicate that for larger latent dimensions, it requires more bits to get close to the image manifold. And this is actually consistent with something that's been observed for VAEs, that as you increase the latent dimension, then it starts putting more of the probability mass on garbage samples. And so those garbage samples prevent you from achieving a low rate. But if you do the same thing for GANs, so as you increase the latent dimension of the GANs, we're essentially pushing the curves up and to the left. So if you're willing to pay a large number of bits, then you can achieve a much lower distortion using a larger model. But interestingly, in the low rate regime, right, if you only pay a small number of bits, then it doesn't get any worse. So in the low rate regime, the large GANs basically behave like small GANs. And so it's a very interesting kind of phenomenon. So even though VAEs introduced this trade-off between rate and distortion as you increase the size of the model, bigger GANs just seem to be strictly better. So that's what happens as you make them wider. If you make them deeper, you're shifting the curves down. So you can achieve a particular distortion using a smaller number of bits. So it's interesting that width and depth seem to have very different effects on the rate distortion curve. I don't know exactly what to make of this, but this seems like a very interesting thing to follow up on. We can compare VAEs and GANs, and the conclusion actually comes out fairly inconclusive. So some models are better in some parts of the curve, others are better in other parts of the curve. So whereas when we looked at log likelihoods earlier, the VAEs seem to be much better than the GANs. When we look at the entire RD curve, the picture seems to be much more nuanced. We can also look at the effect of algorithmic choices. There have been lots of different GAN models proposed. And so what happens if we use different regularizers for the GAN, gradient penalties and things like that? And so we see 3 kind of clusters of curves here, one for the 5-dimensional models, one for the 10-dimensional models, and one for the 100-dimensional models. So the algorithmic choices have kind of a subtle effect, but most of the difference here comes from just making the models larger. Right? And it's kind of consistent with the recent history of GANs, right? Big GAN kind of just made the model very big and got rid of a lot of the tricks that people have been using to train them. Okay, so AIS, it can give very accurate estimates if you wait for a long time, but it's also very expensive, right? It could take a day to generate one of these curves for a CFAR. So one question you can ask, in fact, the reviewer asked is, well, maybe it would work just as well to train an inference network. So do inference using an inference net instead of AIS. And for VAEs, this sort of works. So the blue curves are the ones estimated using AIS. The red ones are estimated using the variational method. And because these are both upper bounds in the true RD curve, we know that the AIS ones are better. But the red ones are reasonably close. This might be good enough, right? So that might be a reasonable way of evaluating VAEs. But if you try to apply that to GANs, you get complete garbage. So the RD curves estimated using the variational method look nothing like the true curves. And in fact, they don't even have the right relationship to each other, so you can't use this to compare the different models. All right, and
Roger, it probably makes sense to wrap up pretty soon.
okay, so I think this is the last slide. So it's another question we can ask. So I've been using squared error so far as the distortion metric, but maybe you can use a distortion metric that's more semantically meaningful, right? So what if you instead use squared error on the hidden representation of a classifier, right? People often justify inception scores and FID in this way, right? You've trained a classifier, it's learned interesting semantic information, so you probably want to compare the distributions in that space. But when you actually compute the RD curves, you get essentially the same results, whether you're using pixel-wise mean squared error or mean squared error on the classifier representation. So these are the curves comparing different shallow GANs. These are the curves comparing the different models, the VAEs, the GANs, and so on. And so whichever metric you're using, you get essentially the same results. And so this seems to be fairly robust against the particular choice of distortion metric. Right, so this gives a way of quantitatively evaluating implicit generative models using well-established statistical criteria. And so instead of just getting a single likelihood value, you can actually trace out the entire rate distortion curve. You can get rigorous estimates of the error in your model using BDMC, and we can learn a lot more than we can just from a scalar log likelihood value. So I'll open it up to questions.
Okay, great. Yeah, so feel free to ask Roger some questions, and thanks again, Roger, for an interesting talk. Let me just open it up with the first question on. This reminds me of things like when we talk about like model comparison and comparing how good like a Bayesian or probabilistic model is, and now you're kind of it feels a bit like when you're comparing different models, like how a bit like comparing apples to oranges versus the belief that among one model class lower scores tend to be better. So what's your just again your take on how to compare them among different models?
Right. So, I mean, there's no one universal criteria that we should always use for comparing different models. And so, maybe likelihoods measure some things you're interested in. If you really are interested in generating samples, then things like FID are probably the criterion you want to be measuring. And so I think there's no one measure. I think looking at the RD curves tells us more than the likelihoods tell us.
Okay.
Gives us more dimensions of information. But I don't think this is like the one magic thing we should always use. But I think we can learn things from this that we don't learn from the other criteria that we're currently using to evaluate generative models.
Right.
The criteria we're currently using to evaluate the implicit models.
Right. So, okay, and then there's a question on what if the data is a language?
Yeah, so we haven't looked at language. I guess, so everything I've talked about so far has been with continuous input spaces. So we relied on being able to use HMC as the inference algorithm. So if you want to apply this to a discrete domain, then you'll have to use a MCMC operator that can handle discrete spaces. You'd have to come up with the distortion metric that you trust. But I think conceptually, it would still make sense to apply this to discrete data, just be challenging algorithmically. Okay.
Yeah, I mean, for discrete data, there's also, you can actually just compute the log likelihood in many of the models. So you don't have to look at approximate scores.
Right. Can we do that for GANs?
No, I don't know how this is done with GANs. But yeah, this is a question of how well they do on language data as well. Yeah, there's another question of, why do the GANs and not the VAEs do worse with the inference networks versus AIS?
Yeah, it's a good question. So you might expect, let's see, so So AIS was better in both cases. It was quite a lot better for the GANs. It was only slightly better for the VAEs. And I would expect it's probably because AIS is giving the correct answer. So we validated these curves using BDMC, and the errors were small enough that they would barely be visible if we plotted them. Okay. So I think that that AIS is probably giving the correct curve, and so we're basically seeing how accurate the inference networks are. And for VAEs, they were trained with an inference net, and so even though the inference net that we're training to generate these curves is not exactly the same as the inference net used to train the model, I think the fact that it was trained with an inference net kind of regularizes it to be easy to do inference in. And so they seem to be just easier to train inference nets in general, and in fact, easier to do inference in general. So AIS seems to have an easier time with the VAEs than with the GANs.
Okay.
You get away with fewer distributions.
Okay. Any other questions? Yeah. If not, let's thank Roger again. I'll just thank everyone on your behalf for an interesting talk.
Thank you.
And yeah, and thanks for showing up for the New Directions workshop. Okay. All right. Bye.
Bye.